Okay, in this video I'm going to try to go through all of normal distribution and what you need to know for the black textbook, or the maths, the Haese Mathematics AA textbook, chapter 21. And we're going to look through pages 505 to 530, and then after going through some of the definitions and discussing the importance of those and a few questions from the textbook, we're going to try some random questions off Revision Village. These have just been picked totally by me at random, easy, medium, hard ones, and hopefully they'll answer most of your questions on this chapter. So, introduction to the normal distribution. Well, the normal distribution is for a continuous random variable. So continuous means that, in this case here, they're saying P of x equals 0 for all x. Well, what does that mean? That means the probability of pinpointing an exact value for x within a continuous curve is next to 0. It's like you're running around a field, and, for instance, the chance that you get exactly running around the whole length of a field, a 30-second point, 2, 3, 4, 5, 6, I don't know, whatever, time is 0. Because you can go infinitely deep into timings, and therefore, in general, we're going to say it's 0, but really this is more of an approximation because, well, technically you could possibly get, what did I say, 30.2, 3, 4, 5, 0, whatever, could technically have a chance of occurring, but it's so minuscule that we're going to say it's equal to 0. So we're looking at a continuous curve. So basically all of our values within this, we're talking CDF, or cumulative distribution function, in terms of questions. What it gives you next, so I'm going to just circle what's important, what's not. So this here is important. And so now we're talking about probability density function. That just means that, imagine you've got a function or a curve. The probability to land something between C and D on that curve is just the area underneath the curve. That's all this is saying. This is not that important. The domain of a function between A and B is 1, yes, but you already know that from the previous chapter, that probabilities add up to 1. So, not that important. I'm going to circle that in red. Actually, even better, we're going to cross it out. Okay. In the case of a normal distribution, this is where we do start to get important. It is continuous. And importantly, it is also symmetrical. So both continuous and symmetrical. So it's continuous and it's symmetrical. And we're talking bell-shaped curves. Well, the reason it's bell-shaped is because it looks kind of like a bell, if you imagine. Except importantly, we have an asymptote here at 0. So the curve will never cross the line 0. It's the most important distribution in statistics, maybe, maybe not. It's fairly good at describing things, and that's what we're going to see now. So, in this question, I've just picked this off your first exercise in the chapter. Discuss whether the following variables are likely to be normally distributed. Sketch a graph to illustrate the possible distribution for each variable. We might give that a go. Let's see. So the first question here says the ages of people at a football match. Well, that is very much continuous, because the age of somebody could be anywhere between 0 and 100, and then within there we've got, months, days, years, so on and so forth. So definitely continuous. However, is it symmetrical? So it's continuous. However, is it symmetrical? Well, let's think about it. If people are going to a football match, what ages do you reckon that they'll be? My guess is that they're going to be on the younger side. And so, in other words, if I were to do a normal distribution of this, and let's say my age goes from 0 to 100, and how high the curve goes is how many people, or the number of people. let's say there's going to be very, very few at the age of 0, and then we might have a huge increase from 20 at about the age of 20, lots of 20-year-olds at a football match, and then maybe we might see a decline after the age of 40 of people at a football match, and then going right the way down and tapering off. So the ages of people at a football match, yes, it's continuous, however, it's not symmetrical. And so therefore, it's unlikely to be normally distributed. How am I going to do this? Okay, I'm going to use C for continuous. So C, it's continuous, not symmetrical, and so therefore it's not normally distributed. Let's look at the next one. So distances recorded by a long jumper. I don't know that anybody here has actually done a long jump before, but it's where you have a pit and then the person dives into the pit feet first and go from a starting block onwards, and however far they jump from this point onwards is measured is measured in terms of meters, centimeters, millimeters. So is it continuous? Yes, it is continuous. Is it symmetrical? Well, I'm not sure what the mean value is in terms of distance for long jump, but let's say it's 2 meters. Well, if it were 2 meters, I could see this being symmetrical, because most of the people will be around that 2 meter mark, and then you might have a few people up here. This is like your Olympian or your Olympic long jumper, and then maybe, people on the lower end. You could have, I don't know, again, your 1-year-old or something, or someone who's very old trying to jump, and so it could be normally distributed. So we can say it's likely to be normally distributed. So in this case here, yes, symmetrical as well, and therefore normally distributed. Numbers drawn at a lottery. Well, numbers drawn at a lottery, imagine that you've got all your numbers. I think a lottery is from 1 to, or whatever. It's just 5 numbers, I think, and you pick them from 1 to 9, and then they turn up. But if you think about it, from 1 to 9, 2, 3, all of these numbers will have an equal chance of being picked. And so therefore, is it normally distributed? No. Because there's no bell shape here. So that's an example where it is symmetrical and it is continuous, but it's not normally distributed. So continuous, symmetrical, not normally distributed. Question D here. So the next question here talks about the lengths of carrots at a supermarket. I'm not sure what lengths carrots are at a supermarket, but I would assume that to be normally distributed. Well, although it does depend certainly on where your carrot's from. For instance, in a more fertile country or from a more fertile farm, they might be slightly longer, but in general, I think you could probably find a mean for the length of carrots, and then there'd be either side of that mean. So I'm going to say that one there is continuous. It's also going to be symmetrical-ish and normally distributed. Rather than do more of these, let's go on to the next question. I think we get the picture. So these are some definitions now. If x is normally distributed with a mean of mu and a standard deviation of s, then we write x is distributed with a normal distribution with mean mu and variance sigma squared, where mu is the mean and s is the standard deviation. This is not included in your formula booklet. Not in formula booklet, strangely. Very little of this chapter is in your formula booklet. And so that's something very important to note, is that this is not in your formula booklet. Whereas binomial is in your formula booklet, which is rather strange that they would choose binomial but not this. In fact, this whole probability density function is also not in your formula booklet, and unless they give it to you in a question and specifically walk you through it, I don't expect that ever to turn up. It hasn't turned up before in any way, shape or form, and the only place I've ever seen it is in this textbook. And you can go through all the past paper questions. I've never seen a question which wants you to use that function. And you definitely do not have to have it memorized, and it's not in your formula booklet. So we'll ignore that. But it is helpful here if we're looking at the diagram, because if we were to plug in x as mu, well then, if we plugged in x as mu from here, we would get this point here, x equals mu. Would give us that if we plugged it into our function. Or let's put down f of mu. And that just shows us what a bell curve looks like. That's just a general form of a bell curve. Some important points here, though, is that the maximum occurs when x equals mu, that the x-axis is a horizontal asymptote. I mean, it's kind of implied that f of x is greater than 0 for all values of x. And of course, it's symmetrical. We discussed that already. This is interesting, though. So your standard deviation is kind of a measurement, a generalized measurement of how much your values will differ from your mean. And so the points x plus or minus the standard deviation are in fact points of inflection. And you can kind of see that on your graph, that between those points we go from concave to convex. So concave, or from convex to concave to convex. So they're quite important points on your graph. Okay. So, are we still on part A? I think we are. So the next question here, to do with our understanding of a normal distribution, is it says x is distributed normally with a mean of mu and standard deviation sigma, and it's giving us that mu equals 4 and sigma equals 3. And now it says in the question, copy the graph on the same set of axes and sketch the distribution for the curves A, where you've got mu plus 2 and sigma squared. Well, the standard deviation hasn't changed in that case. All that's happened is that our mu value has increased by 2. So all we can expect here, if I'm able to draw it, is a shift along by 2. Shift. If we've got 2 sigma squared, what we'd expect are these points here, which are at plus or minus mu plus or minus sigma, because we've looked at this as mu. So the center point is mu. And then in this case, we've got mu plus sigma and mu minus sigma. So if sigma's just increased, that means that we're going to widen outwards. And so our curve would still have the same value for mu, but in this case here, we would widen out. Something like that. Let me try to give you some exact values as well. So if we're widening out, and this here is our new value for sigma, then we can expect our value from 1 to go from 1 to that, or 2. Sorry, it's minus. So minus 2. And our value from 7 to double as well, squared. So it's basically going to be pushed outwards. One other point of note is that I made a mistake here. And my mistake is that I've included all this area. Well, all the area under the curve has to be equal to 1. And so therefore, your value in the middle has also got to be dipped to keep the area under the curve the same, because the whole area under the curve must be equal to 1. In this case here we've got a shift and it's dampened, so therefore we're looking at like that. So again, mu has been shifted on by +2 and everything's been sort of pushed down. Question D, similar case, except in this idea our sigma's been pushed inwards, so let me just kind of draw these on the diagrams. So mu has moved. In these cases, these ones have moved outwards because sigma's increased. In this case here, sigma has moved inwards because we've got a third or a ninth of sigma squared. And so all of sigma has been divided by 3. And to keep the area under the curve the same again, we're going to have a very steep upward curve. In this case here, we've increased it by 3 mu, and we've made it steeper, so it'll look like that, because it's kind of like we're squishing it. So it's a squish and a shift. Great. Part B, calculating probabilities. I'd say everything in Part A is helpful, but at the end of the day, what's going to gain you marks is being able to calculate the probabilities using your normal distribution. So, you don't really need to know any of these numbers. This is all totally irrelevant, but it's interesting. And that is that between your mu minus sigma and mu plus sigma, you've got about 68%, and then going outwards, all of this should add up to 1 as well, but you don't need to know the standard curve either. So this is also from your textbook. Not very necessary for questions that you do, but it's still interesting to look through and to see an example of a curve. And these will be the same regardless of your values of mu and sigma. We're going to look at calculating probabilities in questions later, but a general idea is that you go onto your calculator and you would use your statistics function, so that's under main menu for a Casio CG50, and then after main menu you go to statistics, after statistics it will give you a list for values, then we've got to select distribution, mine just says dist. After that, feel free to use your textbook for finding these if you do not have a Casio and you've got one of the other strange graphical calculators. And F5 distribution, and then F1 normal. And once you click on that, the main one that we're going to be using is NCD and inverse norm. So under there you'll find your NCD and inverse norm. So let's put this down like that. So in there we're going to use F2, NCD, or F3 throughout this video. Okay. The standard normal distribution. This is where it really gets fun, and this is what really makes the chapter quite difficult as well on the flip side. And that's the fact that they want you to approximate your values for, or not approximate, they want you to transform your values for mu and sigma into the Z distribution. Well, the Z distribution is just your standard, well, we call it the standard normal distribution because mu, in our case, is 0, and sigma is now 1. And the reason why this is so powerful, this transformation, is back in the days before you had a calculator to find all your numbers and to give you your values for probabilities with your distribution, what you would do is you would transform it, whatever your distribution was, you transform it to the general Z distribution, and then you could look up all your numbers with tables, which before a calculator like these existed that does everything for you, was quite handy for finding values, and then you convert it back at the end. So it's a bit of a long-winded process, but we're also going to use it in different ways as well. But that was initially why it was sort of created and thought through as an idea, was to standardize everything. So every normal distribution can be transformed into the standard normal distribution, or the Z distribution. And so this is our Z distribution. But all of this will become much more clear when we do it with questions. I found this question quite interesting from your textbook because it shows you this curve again that we were looking at earlier. We looked at this curve, and I think it's good for understanding, although it's not the sort of question that could turn up on a past paper, really. But use the diagrams to calculate the following probabilities. In each case, sketch the Z distribution and shade in the region of interest. Well, if we can transform our values to the Z distribution, then we can find all our standard values. So in this case here, Z is between -1 and 1. Why does it not matter that they're greater than or equal to, or just greater than? Because P of X equals 0 anyway. So does it matter if it's less than 1 or less than or equal to 1? No, it doesn't. In this case here, between -1 and 3, so we're going to include all of that, -1 and 0, and you would just add up the probabilities underneath the curve there. If you want to do this less than 2, so everything here, greater than -1, greater than or equal to 1. And so that there is your probabilities in a nutshell. The reason why they don't give you any numbers past here is because you're going to get 0.00000, maybe 1, something or other. And so the region from here to here, for instance, doesn't matter in our calculations because it's so small that it's irrelevant. Okay, the last section that it wants you to do is on quantities, quantiles, and this is basically implying your inverse normal distribution, applying. So if you want to practice applying your inverse normal distribution, then that's part D. Well, now we get on to the fun stuff, which is past paper questions, and that's really the main reason to watch this video. These have all been taken off past papers in the last 4 or 5 years, and so they're all fairly recent examples of how this could turn up in questions. Pretty unanimously, normal distribution is a paper 2 topic as well. So, the first question here says, random variable x is normally distributed with a mean of 90. The following diagram shows the normal curve for x. Let R be the shaded region under the curve to the left of 84. The area of R is 0.22. So in fact, this may even be an example, I might eat my words here, of a question where you won't need a calculator, but let's see. So write down the probability that x is less than 0.84, well that's just given in our question because it's the area under the curve that we looked at the beginning, and so therefore that's just 0.22. Because it's the area under the curve here, is what measures the probability. So the total probability under the curve is 1. Find the probability that x is between 84 and 90. Well, if we think carefully, 90 here is our mean, and so 90 here is the midpoint of our curve, and so that means that everything above 90 would be equal to a half. And everything below 90 would be equal to a half. So all of this region here, so this is my 0.22, all of this region here is in fact 0.5 because it's symmetrical. So it's going to have equal areas, both sides of the mean. So find the probability that it's less than 90, well, that's just going to be 0.5 minus 0.22, which is 0.28. Okay, this is an extremely rare paper 1 question. Okay, let's look at the next question. Between 84 and 96, well, if we look closely at our graph again, 84 to 96, 96 is also a distance of 6 away from 90. And so therefore we can assume that this area here, which we worked out as 0.28, is going to be the same as this area here of 0.28. And so adding those both up together, we're going to get 0.56. Okay, first question done. That was easy. Next question. A random variable x is normally distributed with a mean of 70 and a standard deviation of 7. Okay, so a mean of 70, a standard deviation of 7. So my mean is here, and then my standard deviation is the inflection point. Remember when we were looking at that earlier? And our standard deviation is going to lie about there. But that's not that relevant yet in the question. So find the probability that, on the diagram, shade the region from x between 55 and 75. So that's going to be this region here. Find the probability that x is between 55 and 75. This is where we're going to use our normal CD function, which we find by doing all of this calculator stuff up here. So I'm going from main menu to statistics, to distributions, to normal distribution, and then to the cumulative normal distribution in this case. And so if you go on to cumulative normal distribution, and then again you click var, or variable, as put in our lower bound, so my lower is going to be 55, my upper is going to be 75, my value for sigma is 7, and my value for mu is 70. And so when I plug all of that into my calculator, I get a probability of 0.74641, something or other, and so therefore we just get 0.746, so 3 significant figures. Given that the probability of x greater than q is 0.15, find the value of q. Okay, well, in this case here we're going to use our inverse normal distribution because we're given a value, but we're not given what q is. So we don't know what our q refers to. And that's why I'm going to show you how to use the inverse normal distribution. So we expect it to be somewhere, I don't know, around here. It's q, so that the area here is 0.15, if that makes sense. And that's what we're looking for. So, on your calculator, we need to use the inverse normal function. So that was by going from main menu to statistics to F5 distributions, inverse normal, normal and then inverse normal. So that's where we're at. And then on inverse normal, if we're using a Casio calculator, so let me get it up. Distribution, normal, inverse normal. And again, we're working with variable. It'll give us the tail, whether the tail is to the left or to the right. In our case here, is the tail going to be to the left or the right? Well, we're actually at the right-hand side here. And so therefore the tail is to the right. So switch that to the right. And then area, what's the area under the curve? The area under the curve here is going to be 0.15. What's my value for sigma? Still 7. And what's my value for mu? 70. You could also have the tail to the left, but what we have to do in this case, if it was in the left, then the area under the curve would be 0.85, because it'd be the opposite of that. And if we click execute there, I get x inverse, it tells me, is 77.255, something like that. So if we're doing 3 decimal places, 3 significant figures, we'd have 77.3. Great. Next question. Time taken for a student to complete an exam is normally distributed with a mean of 40 and a standard deviation of 5 minutes. Actually, something I'm going to do with these past paper questions, I've just realized, is I am going to take a photo of my calculator screen that I'm applying, and I'm going to post that on the video at the end. So let me just do that for the other one. That's what we did the other one. Great, so you've got a copy of that. Next question here. It's telling us the time taken for a student, I think this is a medium one now, for a student to complete an exam is normally distributed with mean 40 and a standard deviation of 5.5 minutes. A student is selected at random. Find the probability that the student completes the task in less than 48 minutes. So I'm going to write down my distribution. This is immediately worth 1 mark. I'm using my normal distribution with a value for mu and a sigma. So mu is 40 and sigma squared is 5.5 squared. So the question in part A is asking us for the probability that x is less than 48. Okay, well, again, we're just going to use our normal CD distribution like we did earlier by going along main menu, statistics, F5 distribution, normal CD. It's basically, that's all you use for this entire chapter in terms of calculator functions. You use one or the other. So in this case, it's that one. So there I'm going to place my lower bound, and this is where it gets more interesting, as a huge negative number. Why do I place in some huge negative number? The reason being is because if you think about the curve, the lower I get, the smaller my value is going to be. So if I place like negative 1,000 or negative 10,000, all of this stuff up to here is actually going to be basically like 0.0000, and it's just going to continue. It's so small, it's marginal, and so it doesn't matter in our curve. And so all I want is the area less than 48, which is going to be less than this. And so I'm really looking for everything down to whatever minus 1,000 is, because it's just, you're taking out that factor. You're giving it an area to calculate under. It's like you're calculating under the area of the curve, but anything below that point is so small that it doesn't matter. And then my upper, I'm going to put down as 48. So my upper limit as 48. And then if I place in sigma in this case, we worked out that sigma from the question is 5.5, and the value for mu is 40. And then when you click the button on your calculator, you will get P, and then it tells you Z low and Z up. So that's telling you the Z values for 48, and in my case, I put in minus 1,000. And so the key number is that we're looking for the probability, and in our case there, that is 0.927 to 3 significant figures. So if I take a photograph of my calculator again, so that I can post it at the end of the video, so that you can see how I've done it, for those of you who need that. Part B, I think is the first time that we're going to use the Z distribution, but it might not be. I think it's just another inverse normal question. So the probability that a student takes between k and 48 minutes is 0.4. So that's the probability that a student X takes between k and 48 minutes. So that's P of 48, P of X, sorry, less than 48, minus P of X, minus P of X, less than K. That's how I would think about the question. And the reason I can split that like this is if you imagine that my curve looks like this, and so I'm taking it from 48, which is slightly above my mean, so that's 48, and then my value for K is going to be about here. Then all of this is my probability in between, and so how could I find that probability? Otherwise, I could just say that we'll take everything less than 48, and if you take away from that everything less than K, sorry, this is rather rough, what you're going to be left with is this section in the middle, basically, if you think about your probabilities, because it's area under curves. So that's one way you can split up your probabilities. Very common, and that's usually what the questions want you to do in these cases, although your cumulative distribution does give you a lower bound and an upper bound. But because K is unknown, and we know what P of X less than 48 is, I've taken P of X less than 48 outside of the question and done it like that. So, if we look at what the question's giving us, it says that the time taken, the probability is 0.4. So we know that 0.4 will be equal to 0.972 or 927 minus the probability of X less than K. And so that means that the probability of X less than K rearranging will be 0.927 minus 0.4, which is 0.527. Again here, we're going to use my inverse normal distribution. In this case here, we don't know what my lower bound is, or my upper bound, and so that's where we're going to use it. So again, go to distributions, normal, F3, and then if you look at your area, my area is going to be 0.527, and then my value for sigma here, we also know is 5.5, and my value for mu is 40. And so when I click execute there, I get the value for my inverse norm as k equals 40.4. Okay, let me just take a photo of those then. So that's what I get, and then if I execute, I get. So I'm going to get k as my issue with this question really is the fact that because we calculated this number previously, if that number was slightly more exact, we would have more difficulties, because all I've done so far is I've plugged in 0.572. If I made that more accurate, I might get a slightly different result. And usually what mark schemes will give you is they'll give you a margin for error. So that means that our margin for error might be between 39 and 41. And that's quite common with normal distribution questions, because accuracy makes such a big difference, especially when you're at the center of the bell curve, because the amount of area between the 2 points can make a really big difference. Okay, let's do the next question then. So this was one of the hard ones that was on the list, and so let's give it a go. So it says, it is given that 3 in 10 men take less than 220 minutes to run a marathon. It is also known that 1 in 5 men take more than 27 minutes to run the same distance. Okay, 274 minutes to run the same marathon. Okay, they're both running a marathon. Assume that time is taken in minutes for men to run a marathon is modeled by the normal distribution and find the mean standard deviation for this curve. So in our case here, let's say that X is distributed, and this is men running a marathon, and for the men running a marathon, we're going to normally distribute it with the mean of mu. Maybe the mean for a marathon could be 250 minutes or something, and sigma squared. We don't know either of those, and that's where our Z distribution comes in handy. So just a quick reminder, our Z distribution is that Z is normally distributed with a mean of 0 and a standard deviation of 1. So in our case, if P of X is less than 220 minutes, we're going to convert this to our standard normal distribution. And this is given to you in your formula booklets. And what's given to you on your formula booklets is that your value for Z is X minus mu over sigma. It's the only thing in this chapter that is given to you on a formula booklet. The rest of the chapter is totally unknown in that regard. So you'll just have to work. From what you know. But if we convert this to our standard normal distribution, we can compare both of these values. So let's convert it. The way to convert this is we need to do X minus mu over sigma as our value for Z. And so we're looking at P of X minus mu over sigma less than, in our case, 220 minus mu over sigma. And that's transforming it. And therefore we can rewrite it as P of Z is less than, well, I'll go on big Z, I won't put the small line in there, 220 minus mu over sigma. And what do we know in this case? We know that it takes 3 in 10 men take less than that, so the probability therefore would be 0.3, versus in the other case we've got 0.2. So we know that this all gets us to 0.3 in this case. And so again, we're going to use our inverse normal distribution. We're going to use it slightly differently. And so for our inverse normal distribution in this case, we are going to write tail to the left, I'm going to assume, but it shouldn't matter anyway. So if you then create your tail to the left, and then the area under the curve will be 0.3. And because we're working with the standard normal distribution, sigma is 1 and mu is 0. And so when we execute that, I get minus 0.524. So in this case here, we've got 220 minus mu over sigma as 0.524. And that's by using my inverse normal distribution on this. So I'm going to take a quick photo of that again, so that you'll have it for your notes when you go through this. And all I've done is I've used the standard normal distribution. So this is using standard normal distribution, SND, and the inverse function. The other one that I'm given is that P of X less than 270 is P of X minus mu, again transferring it to the standard normal distribution, less than 220 minus mu over sigma, but not 220, sorry. Now we're working with 270 minus mu over sigma. And so, therefore, that's the same as saying P of Z less than 270 minus mu over sigma is 0.2, because it takes 1 in 5 men that time to do it, and so therefore we know that 270 minus mu over sigma equals changing this area for 0.2 minus 0.842. And again, I'm just taking these to 3 significant figures. And you shouldn't be expected to do any more accuracy than that. So let me take a photograph of my screen again. Because we're working with the Z distribution again, mu equals 1, and sigma equals 1 and mu equals 0. So this is really cool now, because what we're saying is that they have the same mean and standard deviation because they're all running the same marathon, and because the time to take running the marathon is our normally distributed variable, we can assume that mu and sigma are the same. And so we've got simultaneous equations here. So if I take this equation and I take this equation and I rewrite them below, I should get 2 simultaneous equations. And those will be 220 equals mu minus 0.524 sigma, and the other equation is 270 equals mu minus 0.842 sigma. And then we can just solve them normally. So if I take one away from the other, all I'm left with would be 50 equals 0. Let's go back to menu, run matrix, and then I'm going to do 0.842, and so therefore I get minus 0. Oh no, sorry, because we're adding them, yeah, it's going to be positive. Yeah, minus 0.318 sigma. Let me double check my numbers. And so therefore, my value for sigma would be 50 divided by minus 0.318, which gets me to 157.2. Let me double check that number. Something here just doesn't feel quite right. Oh yeah. Yeah. I made a mistake here. This should be 274. So it's exactly the same as it was previously, except we're using 274 in this case. And so we're going to get very slightly different numbers. Let's keep that the same. So let me just do everything with 274. So going back to main menu, run statistics, distribution, normal, inverse normal. Oh, this number's going to stay the same actually, isn't it? We're still going to have 0.824. Okay. I've made another mistake here, and that mistake is that it's greater than 274 minutes. And this is going to make a difference because that means that we're looking for z greater than that value being equal to 0.2. But the way that our inverse normal distribution works is that what we're looking for is, I just felt that my negative number there for sigma was wrong. This is the same as P of 274 minus mu over sigma being greater than z, because probabilities add up to 1 equal to 0.8. And so what I'll get there is a positive. And this is going to change my question slightly, because in this case here I've got a positive mu. If I take the first one away from the second one, what I'll be left with is 50 equals something slightly different. We're going to get 50 equals, go back to our matrix, 0.842 plus 0.524, which is 1.366, and so 50 divided by 1.366 would be 36.6 minutes. Equals sigma. Again, it really counts how much accuracy that you're using. And so when I've done these questions here, my z values technically would have yielded numbers that were larger. I gave those only to 3 significant figures, and so therefore you could expect my answer to be appropriately limited by that. And often there'd be a margin for error there in terms of what your sigma and your mu would be. But if that's my value for sigma, if I take the first equation and I rearrange it, so this is my equation 1, 2, and what I've done is 2 minus 1. And so in this case, if I take my equation 2 and I plug that in, I would get 270 equals mu plus 0.842 lots of sigma, which is 36.6. And so if we plug that in, we would get mu as 270 minus 0.842 times 36.6, which is 239.2. I'm going to give a 1 decimal place here. Although because I've taken it earlier, I should probably be more careful with that. 3 significant figures. Okay. The final question then on your paper that I wanted to go through in this clip is one of the last ones, hard question worth 15 marks. And so you'd expect to be doing at least 15 minutes worth of work, which is a substantial chunk of your test paper. That's a sixth of your test paper time, because you get an hour and a half. So a pencil manufacturer measures the length, sorry, but it's not a mark a minute, so that's even more than a sixth of your time. It might be closer to a fifth. But the pencil manufacturer measures the length L of their new batch of pencils. The lengths of the pencils are normally distributed, so that means they follow the bell curve, continuous, symmetrical, all the rest of it. And they're giving us our value for mu, but we don't know our value for sigma. So they're telling us find the probability that L is between 110 minus 2 sigma and 110 plus sigma. Well, let's dissect that further. So if I write it down, 110 minus 2 sigma less than L, 110 plus sigma. What do we notice here? We notice that that's my mean in both cases, and then I have a standard deviation in both cases involved. And so from experience, and this is something that you might not be able to see quite so easily, but from experience, I can see there that because they both contain the mean here, I can get rid of that mean mu if I apply the z distribution, and so it just simplifies my problem. So if I do that and take this as my value for x, this is the same as p of x minus mu over sigma being less than L, less than, what's x1, isn't it? x2, or L2, minus mu over sigma. And so if I plug my values in, I would get P of 110 minus 2 sigma, that's my value for x, minus mu, which is 110, over sigma is less than L, is less than 110 plus sigma minus mu, which is 110. Over sigma. And so therefore, if I simplify that down, 110 minus 110 is going to give us 0. All we're left with there on the first one is minus 2, is less than L, and on the second one is 1. Okay, so I'm working with my standard normal distribution. What I've done is I've changed this from x being distributed with a normal distribution of 110 and sigma that we don't know, sigma squared, to x distributed, z distributed, with a normal distribution of 0 and 1. And so because of that, I can find my value here, because I've got everything I need. I've got my sigma, I've got my mu, I've got my sigma, and I've got my lower and my upper bound. So if we go along to statistics, distribution, normal distribution, and cumulative normal, again we're working with variables. My lower bound is minus 2. Where's the small minus? Minus 2. My upper bound is 1. My value for sigma is 1. My value for mu is 0. And so what I get at the end here is 0.81. 9 to 3 significant figures. So we'll round up from 5 to 9 there. And so again, let me take a photo of my calculator screen. And so when we click equals, we got that. Notice when you click equals in this case, your z lower and your z upper stays the same because we're using the z distribution. Again, the power of the z distribution cannot be matched. Find a probability that, but that's quite a hard one to see unless you've kind of done a lot of these and converting between your z distributions. Find a probability the length of pencil is less than 116. Pencil is less than 116 millimeters is 0.95. Find the value of sigma. Another case of applying our z distribution because we don't know what sigma is. And so P of x less than 116, and they're giving us that that is 0.95. So that means that what we've got is we have, if we convert this from our distribution that we're using, which is the, all of these should be said. We've changed L into Z in these cases. So again, we're starting with our x or L distributed with the distribution in question, and we're converting it into the standard normal distribution. So in this case, P of Z will be less than 116 minus whatever mu was, which is 110 over sigma. And we know that equals 0.95. So 0.95 is not a Z value. It's a probability. And so what we really want is we want to find the Z value such that the probability that Z is less than that Z value gives us this 0.95. And so to do that, I'm going to have to use the inverse normal distribution on 0.95 with mu as 1 and mu is 0 and sigma is 1. So if I take the tail to the left and I write down the area, which is 0.95, mu and sigma as 0 and 1. When I click execute there, I get 1.6448 something or other. So the aim is we'll round up. 44, so we'll just leave as 1.64. So 3 significant figures. And that there is going to be equal to 116 minus 10, which is 6 over sigma. And so therefore, going back now, switching between running matrix and statistics, 6 divided by 1.64 gets us to 3.658. As always, we're going to get a more accurate answer by doing more decimal places. So if I were to give a couple more there, 6, 4, 5, 8, I think it was. I get a value that is actually, I think it's 6, 4, 8, something or other. I get a value for sigma that is 3.65 to 3 significant figures. Okay, let me make sure that I wrote down what I wrote down previously. Okay, part C. A pencil is, all pencils with at least length of at least k millimeters are classified as large pencils. A pencil is chosen at random. Find the probability that the pencil is a large, it is a large pencil. Probability it is a large pencil is 0.6. Find the value of k. All pencils with length at least k millimeters are classified as large pencils. All pencils with probability at least k are classified as large pencils. So we need the probability of our pencil, which they're saying is L for the length of a pencil. L and X I've interchanged in this question. Is greater than K is 0.6. So this is a classic case of inverse normal distribution, and we're going to place in tail to the left, area as 0.6. Sigma we've worked out as 3.65. and mu is going to be mu is going to be 110. Okay, in this case the talus beats the right, because we're working with a large pencil, and if we do that we get 109. Again, this will be on the PDF file. The reason we're working to the right is because we're working for probably the pencil is a large pencil, so anything greater than that value of k, so at least that value k. And so because we're working with probability of L greater than k, we're looking at a distribution where we're working with at least k, where a value k is. But we don't know where our k is. It might even be below the mean, which in our case it is, because I get, when I click equals, I get the value for k as 109. That's it, to 3 significant figures. Don't forget to add in your millimeters here as well for your values. Okay, part D, part I. A pencil is chosen at random from the large pencils. Find the probability that the length of the pencil is less than 111 millimeters. I kind of just worked that out by accident now by doing the left-tailed test, but it's not quite exact. A pencil is chosen at random from the large pencil. Find the probability that the length of this pencil is less than 111. So it's chosen from the large pencils. Find the probability it's less than 111. So now we're using a bit of conditional probability. That's fun. So we need to find the probability that it's less than 111, given that it is a large pencil, which we worked out is 109. So we need the probability that it's less than 111, given that it's greater than 109. Well, what do we know about conditional probabilities? We know that this is the same as P of both of them, so P of this one and that one. So probability of both of those in this case is L is greater than 109 and 111, that satisfies both, over the probability of B. Conditional probability definitions here. So all I've done here is I've used conditional probability. So P of A given B equals P of A and B over P of B, which I think is given to you in your formula booklet. Okay, well we know what the bottom one is. The bottom one is just 0.6 because that was given to us in our previous question. That's this. The top one, however, is one we need to work out. So for that we're going to use the cumulative normal distribution. So if I use the cumulative normal distribution, let me go back to that. And then my lower bound is going to be 109. My upper bound, 111. My value for sigma, 3.65. And my value for mu as 110. And when I plug that in, what I get is 0.216. And that just continues but 0.216 over 0.6, and that gets me to menu run matrix 0.216 over 0.6, I get 0.36. Exactly. Great. And so there's my value for that probability. Part 2 of D. 20 pencils are chosen at random from the large pencils. Find the probability that at least 3 pencils have length 111. So 20 pencils are chosen at random from large pencils. So how many pencils are we now choosing? We're not just dealing with one pencil, we're dealing with multiple pencils. So what do we need to use? We need to use our binomial distribution. So that's our value for n. What's the probability as part of large pencils? 0.6 is p. And we have a binomial distribution, which is great. Oh no, but they want it to have less than 111 millimeters, but they're part of the large pencils. So in our case here, actually, p is going to be the 0.36, which we worked out in the first part of the question, which made sense. And now we can use our binomial distribution. So x is distributed binomially, 20 pencils, 0.36 is the probability that they satisfy the region given. And then we want to know the probability that at least 3 pencils have length less than 111. So we need p of x at least 3. P of x greater than or equal to 3. It's quite clever how they switch between discrete and normal. That's something that's quite common, but that does make it quite a hard question. So I'm on binomial now, and then on binomial, I'm going to click on binomial CD, and then from there, my lower bound will be 3. My upper bound doesn't matter. The total, 20, is the upper bound. Number of trials, 20 trials. Probability, 0.36. And when I do that, I get 0.9903, something like that. And so in our case here, we just need 0.990 to 3 significant figures. Great. I haven't even checked how long that video was, but somebody walked in and cleaned the classroom during that time as well. So it's certainly been a while. So that was some of the noises you might have heard in the background. But I'll figure out a timing for a video next week, or not a video, a lesson next week, where we can go through some of this stuff online, if you'd like to tune in from your study leave. And I hope that's explained some of what normal distribution is in more depth. I'll upload the PDF and I'll put all the photographs of my calculator in use onto the PDF before I do it, and hopefully get that uploaded by the end of the